So, like Kirsten mentioned, my name is Stephanie Taboada, and I'm an assistant engineering professor over at Suffolk County Community College. And this technology was actually developed at Stony Brook University. And so what this technology does, it's basically a safe way to store and separate hydrogen. And I'll go into why we care about this. All right, so we all know that there's currently a very urgent need to decarbonize due to what we're seeing now with, for example, wildfires in Canada. It's leading to severe weather events all across the globe, massive losses of life. And so there's a huge focus now to find renewable sources of energy. So currently, CO2 emissions represent the majority of the greenhouse gases that are responsible for these severe weather events. And actually, the United States is the second largest emitter in the world. If we look further into the data, fossil fuel combustion represents 90% of these emissions. And natural gas specifically, if we're looking at which fossil fuel is responsible for 35% of these emissions. And so natural gas has long been considered a bridge to the renewable energy, sector. And the reason for this is because we have about 15,000 kilometers of natural gas pipelines within the US. And these connect from state to state and obviously within the state as well. So hydrogen specifically can actually blend with our natural gas that we're currently using. And so hydrogen has, when it's combusted, it does not emit carbon dioxide. It's abundant. And when we look at it from a weight basis, it actually has a higher energy content than any fossil fuels that currently exist. The market size is about 137 billion right now. It's mainly used in the chemical sector with some portion used for storage, right? But we're seeing a huge increase specifically from interest in government right now, thanks to the Inflation Reduction Act. And so we're expecting the market to grow to about 1 trillion in 2050. The problem with hydrogen at the moment is that it's difficult to transport. It's difficult to store, mainly because it's light. And so because it's light, you can't have a lot of hydrogen in what is currently being stored in cylinders. So it's currently being used in gas cylinders and transported mainly in that way. The energy content within that is only about 8 megajoules per liter on a volume basis, versus if we compare it to gasoline, about 32 megajoules per liter. So you can see that there's a pretty large difference there. And the fact that it's light means that it is flammable, so you can have hydrogen escaping into the air. And if that does happen, there can be a fire. Okay, so there around in certain cities, for example, hydrogen is not allowed to be transported at specific times. You can only transport it either very late at night or early morning when there's no traffic. And so myself and my team here, we set out to develop a technology that can address all of these issues. And so currently, like I said, I'm a professor. I'm also an engineering PhD candidate over at Stony Brook University, and that's how this technology was developed through my research. And my PhD advisor is Devinder Mahajan. He's the lead for the lab, also a professor at Stony Brook University, entrepreneur himself, and the director of what is the Gas Institute of Gas Innovation and Technology. Our industry mentor, Makini Byron, she is the director of external technology at Linde. Linde is the world's largest natural gas supplier, and she works specifically in evaluating technologies for commercialization. So she's perfect to guide us and lead us for this type of startup. So without further ado, this is the technology. So you can see here in this image, we have canisters. And so these canisters are lined with what's called a metal hydride. And so these metal hydrides, the way they work is through temperature. So when you cool the hydride, and let's say you have a gas mixture that's flowing through the canister, the hydrides will absorb hydrogen, right? So if, let's say it's hydrogen and methane flowing, the hydride will only absorb hydrogen. And then when it's heated, the hydride will release hydrogen. So what does this mean? This means that we can offer two capabilities. We can separate hydrogen from methane, and we can also store hydrogen in now a solid form. Okay, so now we're not storing hydrogen as a gas or as a liquid. We're storing it in a sort of solid state captured within this metal hydride. So that means that we can offer a safe way of transporting and storing hydrogen. So potentially what we're expecting to do is to build some sort of modular unit here, as you can see to the right. And so this allows for easy scale up. It's the direction the chemical industry is heading right now, building modular plants so that they're easily transported and accessible to really any point in the world. And we went through the NSF I-Corps program end of last year. And there was tremendous interest, particularly from the natural gas utility. And so they are in dire need of a technology like this because they need to be able to separate hydrogen in order to avoid their customers who may be hydrogen sensitive from receiving that. So this is ideal for them, and that was the beachhead market that we had targeted. And we also have, a huge network right now here at Stony Brook University with National Grid, which is our local gas utility, as well as Con Edison. And there are plans to build a demonstration plant in the near future. In terms of competition, so here I have, like I mentioned, gas cylinders, the main way of transporting hydrogen. There's also liquefied hydrogen. And then in terms of separating, it's the most commonly and oldest technology available is membrane. But as you can see here, none of these technologies can offer both. None of them can offer separation and storage. However, we can. The problem that we're encountering right now is cost and also increasing the weight percent of hydrogen that can be stored. So in terms of cost, HISEP, we're using rare earth metals, so that does drive the cost up. And we would need funding to find alternative metals, as well as to analyze the lifetime of the material to determine how long it actually lasts. So in terms of milestones, we're expecting to patent the technology this year. We've already filed a preliminary patent. We're expecting to apply to government grants, and then of course continue optimizing the technology. And then in the second and third year, apply for SBIR, build that demonstration plant that I mentioned, and then hopefully establish a manufacturing partner. And so the goal here today is to develop networks so that we can refer back to in order to raise capital funding, hopefully by the second year, when we're ready to start manufacturing and building the demonstration plant that I mentioned. So I've added here my contact details for networking purposes. So that is all I had today.